Welcome to Chapter 4, where we explore the fascinating world of large language models. LLMs represent one of the most significant breakthroughs in artificial intelligence history. Starting with GPT-1 in 2018, we've witnessed an exponential scaling of model capabilities. GPT-3, with 175 billion parameters, amazed the world with its ability to write coherent essays, generate code, and even engage in creative tasks. Today's models like GPT-4 push these boundaries even further. Let's understand how these powerful systems work and how to use them effectively. What exactly makes large language models large? It's primarily about scale across three dimensions: parameters, data, and compute. GPT-3 has 175 billion parameters, trained on hundreds of billions of tokens using thousands of GPUs. But scale isn't just about bragging rights. As models grow larger, they exhibit emergent abilities, capabilities that only appear at sufficient scale. In context learning, where models learn from examples in the prompt, emerged around 10 billion parameters. Chain-of-thought reasoning appeared even later. Training GPT-3 cost millions of dollars in compute alone, highlighting the enormous resources required. The GPT architecture is elegantly simple. It uses only the decoder part of the transformer. Unlike BERT's bidirectional attention, GPT uses causal or mask self-attention, where each token can only attend to previous tokens. This enables autoregressive generation, predicting one token at a time based on all previous tokens. At each step, the model outputs a probability distribution over the vocabulary, and sampling from this distribution determines the next token. GPT-1 had 12 layers, GPT-2 scaled to 48, and GPT-3 reached 96 layers. Each generation brought not just more parameters, but qualitatively better capabilities. Training LLMs is a multi-stage process. Pre-training exposes the model to vast amounts of text, learning to predict the next token. Data sources include Common Crawl web text, Wikipedia, books, and code repositories, totaling hundreds of billions of tokens. Supervised fine-tuning then teaches the model to follow instructions using high-quality demonstrations. Finally, RLHF aligns the model with human preferences. This training requires distributed computing across thousands of GPUs, sophisticated optimization techniques, and careful data curation. The chinchilla scaling laws showed that we should balance parameter count with training tokens for optimal efficiency. RLHF, or reinforcement learning from human feedback, is crucial for making LLMs helpful and safe. The process has 3 steps. First, collect human preferences by showing pairs of model outputs and having humans choose the better one. Second, train a reward model to predict these human preferences. Third, use reinforcement learning with PPO to optimize the language model to maximize the reward. This teaches models to be helpful, harmless, and honest. Without RLHF, models might give technically correct, but unhelpful or even harmful responses. RLHF is what makes the difference between a raw language model and a useful assistant like ChatGPT. Prompt engineering is the art and science of crafting effective prompts to get the best results from LLMs. A good prompt typically includes a system instructions setting the context, relevant examples or context, a clear task specification, and desired output format. Techniques range from zero-shot prompting with just instructions, to few-shot prompting with examples, to chain-of-thought prompting that elicits step-by-step reasoning. The key is to be specific, provide relevant context, and iterate based on results. Even small changes in wording can significantly impact output quality. Retrieval-augmented generation, or RAG, addresses key limitations of LLMs, knowledge cutoffs, and hallucinations. RAG combines an LLM with an external knowledge base. When a user asks a question, the system first retrieves relevant documents using embedding similarity search. These documents are then included in the prompt, giving the LLM access to specific, up-to-date information it can cite. This reduces hallucinations because the model can ground its responses in retrieved facts. RAG is particularly valuable for enterprise applications where accuracy and source attribution are critical. The open-source LLM ecosystem has exploded. Meta's LLMA and LLMA2 demonstrated that open models can approach proprietary model quality. Mistral, Falcon, and MPT offer various size and capability trade-offs. These models can be fine-tuned on your own data using efficient techniques like LoRa, which updates only a small subset of parameters. QLoRa combines quantization with LoRa for even more efficiency. Open models enable privacy-sensitive applications, full customization, and freedom from API dependencies. The Hugging Face ecosystem provides easy access to thousands of models and datasets. LLMs are transforming numerous industries. Code generation tools like GitHub Copilot boost developer productivity significantly. Content creation workflows leverage LLMs for drafting, editing, and ideation. Customer service chatbots provide 24/7 support at scale. Research assistants help scientists navigate literature and generate hypotheses. Educational applications offer personalized tutoring. Healthcare applications assist with documentation and decision support. Emerging frontiers include scientific discovery, drug design, and creative arts. However, responsible deployment requires attention to accuracy verification, bias mitigation, and maintaining appropriate human oversight. Let's summarize Chapter 4. We explored how scale enables emergent capabilities in large language models. The GPT architecture uses decoder-only transformers with causal attention for autoregressive generation. Training involves pre-training on massive corpora, supervised fine-tuning, and RLHF for alignment. Prompt engineering and RAG are key techniques for effectively using LLMs. The ecosystem includes both closed models like GPT-4 and open alternatives like LLMA and Mistral. Tools like OpenAI's API, Hugging Face, and LangChain make these capabilities accessible. In our final chapter, we'll dive into practical NLP applications: sentiment analysis, named entity recognition, question answering, and more.